All right, though. Let's go ahead and get started with some things here. So far, we have started talking about our essentially step over from where we were, right? A parallel path from where we have been going for the last few chapters here. We've been talking about forces, we've been talking about energy, we've been talking about momentum. Now we're like suddenly flip everything around and then keep spinning it that way, because now we're talking about rotational things, right? Same concepts, but now happening for rotational motion. And when I say the same concepts, there's just a couple things that we need to add on to it. Today, we're adding on a little bit more stuff about forces and mass, or the equivalence for rotational motion. But let's talk about this thing. Any object that is going to be spinning around, and let me go ahead and move myself here a little bit so that we can actually see. Let me put myself up here for now so that we can see those slides a little bit better, because I have a lot of text going on at the bottom. So far we've looked at rotational kinematics, right? Position, velocity, acceleration, those big three. We've talked about how there's some weirdness a little bit to it, but at the end of the day, we can actually pretty readily transform back and forth between those two. All we really need to do is multiply by a radius, and then we're back to our original thing. Now, when we're talking about dynamics, we don't have quite the same description as we did from before. Right? When we're talking about things moving in a circle, well, that's all fine, but like, that's not the complete picture, right? We've exclusively talked about a centripetal force, and that is only the force required to keep an object spinning around in a circle. But that doesn't say anything about the object itself spinning, or how we actually address when we've got other varieties of objects, right? Specifically, we've been looking at like something spinning around in one circle and the object is all the way out there, and that's fine. That is technically rotational motion, but it's not the only thing that we can have. So the moment of inertia is kind of like what mass was to force, right? And of course, it is related to mass. We can see if we're looking at these units, moment of inertia, the units of it do indeed have kilograms involved there. But generally speaking, the moment of inertia is telling us how resistive is something to a torque trying to make it spin. And I'll talk about torque in a minute here, but that's more or less how easy is it to get this thing to spin. A lower moment of inertia means it's much easier to spin. A much higher moment of inertia means it's much harder to spin. Right? But just like mass, light mass versus heavy mass, really it just requires, there's a relative force that must be applied to get it accelerating. Now, actually calculating this is maybe a little bit confusing at first, but it's not going to be too bad. First, it's a little bit nicer that it is simply a scalar value, right? There's nothing to worry about as far as that goes. We don't have to worry about vector signs or anything else really crazy going on here. We only need to calculate a scalar value, but here's what we have to do. We have to figure out what point are we going to be orbiting around or rotating around. And for this picture right here, we've got this black dot in the middle. That's my axis of rotation. These three masses are going to be rotating around that. With that, to calculate the moment of inertia, I'm going to take each individual mass, multiply it by how far away it is squared, and add all of those values up together. Right, so I know that I have an R1 vector, R2 vector, R3 vector, but there is no vector sign down here. It is just the scalar quantity. It is just the distance away from my pivot point. It's a little bit easier to solve, right? And of course, this works very well when we've got a number of masses like this. So let me just kind of jump into a concept check immediately here. Let's think about it like this. Which of these two dumbbells has the larger moment of inertia about the midpoint? So let's say that we're going to spin these things around at the midpoint for each one of these. Which one is going to have the larger moment of inertia? What do we think? One answer so far. Anyone else? Two answers. Both agree that it's B so far. All right. I think that's the train that we're on right now, and I agree with that. And let's talk about why. Let me just write down that equation. Let's kind of see. We don't even need to worry about both of them. What I can say, the moment of inertia is always just going to be essentially some sum of mr squared, right? Let me just look at it like that. Let me not even bother about the full equation. Let's just say the moment of inertia goes as m times mr squared. If that's the case, then I look at these two things. I would say, all right, well, I've got one mass, one radius, and that's fine. Or I've got twice the radius, but only half the mass. Twice squared is 4 times. 1/2 doesn't outdo that 4 times. Dumbbell B should indeed have the larger moment of inertia. Does that make sense here? Now, to tie that all back in with our other information so far, that means dumbbell B is actually going to take a little bit more effort to get it spinning, right? Or rather, if we had put in the same effort, dumbbell A is a lot easier. It's going to spin a lot faster. So, I want to try this thing out. Let's imagine here, you have seen this thing before. And we're going to change this up just a little bit. We're no longer thinking about the center of mass of this object, right? This weird 4-corner thing. We're not thinking about the center of mass anymore. I'm saying that we have a fixed rotation axis. Whatever we have done, maybe we've stuck a post through it. We have made sure that if it's going to spin around that point right down there. What is the moment of inertia of this object as it is right now? I want you to take, say, the next 3 or 4 minutes to calculate this thing out, and then we're going to come back together and see what you got. All right, so let's start taking a look here. So we have our rotation axis axis that we're going to end up using here, and I've even got the old picture from last time still saved in that one. But I want to copy this thing over, just for the sake of it. Let's go ahead and keep that thing with us here, make our lives a little bit easier when we're drawing this thing out. So I'm going to look at these things piece by piece, and let's go ahead and talk about these essentially as we're doing them, right? My full big equation is another summation. What I'm going to say is that the moment of inertia in total is equal to the summation of every single individual mass times its distance away from the pivot squared, which means piece by piece. Let's start with mass A. Mass A times the radius of A squared, that one's 0, right? It's literally on top of the pivot point. It's not any distance away from the pivot point. It doesn't contribute anything to our moment of inertia. Take mass B squared, or mass B, oh, that's a terrible B. Let me just go ahead and write in the numbers here. That's probably a little bit easier. I'll say 0.2 kilograms times my distance, 0.08 squared, plus 0.2 times 0.1 squared. So this is kind of in order here, mass B. I did mass D because it's just a little bit easier, and then I'm in luck because mass C, once I have these two, is a little bit easier. I could say this is 0.2 times square root of 0.08 squared plus 0.1 squared squared. If that's a little bit confusing, let's just go with this. 0.08 squared plus 0.1 squared. That's what that is right there. Right, Pythagorean's theorem would give us this quantity under a square root. If we were to find the actual distance, that hypotenuse, since we're squaring it again anyways, I'm happy to just leave it like that. So this right here is mass C. All of these things summed up together, at the end of the day, we should come up with a value like 0.403 kilogram square meters. So it's a little bit of an extra piece here, but I don't think it's too bad of one. It's mostly more tedious than anything else, right? A lot of these values aren't super crazy to calculate or anything else like that. I've got my point masses, and I just need to find wherever they're at, and it's, you know, mostly geometry at that point. So let's imagine, just for fun, just for entertaining the idea, what would happen if we had so many masses that we couldn't possibly calculate all of them at once? What if there was an uncountable number of objects all put together, otherwise known as a continuous body? The collective scream. Yeah, calculus is always coming. This is indeed calculus-based physics, unfortunately. Right? Unfortunately for you, at least. I love it. But as we're talking about this thing, what is a little bit of a relief for you guys here is that we don't have to worry about a lot of this stuff, right? Realistically, I'm going to give you the most important things here. You're either going to know the moment of inertia, you're either going to have some sort of known shape to us, right? This sheet right here, look at that, right? Let's go ahead and take a look at this real fast. This right here is some of the most common shapes you might see spinning around, right? A cylinder, a hollow cylinder, a sphere, a hollow sphere, a door, a very poorly designed door, a block of some sort. All of these things, much easier now that we have this table right here. Right, looking at this table like this, at any point I could just say, all right, we've got this entire thing. Anytime you see one of these shapes, you instantly already have the moment of inertia. No need to worry. So I do want to talk about how we calculate that, though, right? Of course, it is going to be doing something just like this as well. This is essentially just when I told you that you need some expression for d of m, this is a similar kind of scenario, right? We don't necessarily know what this looks like for an object like this. This is disgusting, if I'm being completely honest. But let me take the hollow cylinder, for example. This is a really, really fun one. So the most important part is my distance away from the axis. The hollow cylinder, all of the mass is a radius r away. It doesn't matter how long the cylinder is, because the long way is not the way that we're spinning around the cylinder. We're spinning around the cylinder about this axis cutting right through the middle right here. And that means the entire thing is just a capital R away. At any given point, I could just say, well, this should be something like R squared dm. Well, all of it's at the same R. R is a constant here. What I end up getting is just my R squared times the total mass. Now, if we have to do it a little bit more real than that, then there are ways to do that. But realistically, these are three-dimensional integrals that I'm not super concerned about. But if you are taking any sort of Calculus 3 or anything else like that, you will see those things, and they're not actually that bad. We will end up using some Calc 3 concepts in 192. Whether or not you have taken the course, kind of like with calculus and some of the derivatives here, if you don't know them already, we're going to throw some things at you real fast and say, well, just use these for now. These are the useful tools that we need. We don't need to worry about the entire class. But anyways, you're going to be able to solve all these problems. I promise. We're not going to have you guys doing any crazy integrals or anything else like that. It's going to be one of these four categories. On a rare occasion, I might ask you to calculate something, but definitely not on the exam, only in the homework, if we're going to be doing that. So, let's imagine something else here, right? What happens? Clearly, in a picture like this, we know that the center of mass is like actually somewhere out here in the middle. We've calculated that, right? So what I had said last time was that an object that is just kind of free floating out in space, that should spin around its center of mass if it's just freely floating. And I'd agree with that, right? And that's a good reason to find the center of mass. However, clearly, things don't have to just spin around the center of mass, right? Look at every door, right? And I keep hinting on this one because in your reading, there's a question about this. But look at every door. Nobody puts the hinges in the middle of the door. It just, like, unless you've got one of those spinning doors, and that's a little bit of a different story, but there's some different stuff on that. I'm talking regular household doors. We put the spinning axis on one edge of the door. Clearly, the center of mass should be right here in the middle. But it still has a moment of inertia. And we need to understand how that moment of inertia is going to change because we are no longer spinning around. We are no longer spinning around that center of mass. And I don't have a revolving door in my house unless you're, well, unless you're talking about the delivery people dropping off food. That's the only revolving door that we've got here. I was going to see if I could come up with some sort of good witty joke for that one, but I've really got nothing on that. But anyways, parallel axis theorem, this is exactly what it is, and this is going to make your life significantly easier than actually calculating this thing out. Here's what it is. If I know I am rotating around some point other than my center of mass, all I need to do is I need to take the moment of inertia that I would normally have around the center of mass, and I add to it the total mass of the object times d, where my pivot point is away from the center of mass, squared. That's it. So we can take this example, right? We are given both of these quantities down here already on a table, but let's kind of prove that the whole thing works. We would say, all right, well, if a rod stabbed through the center was spinning around and has a moment of inertia 1/12 ml squared, I would take my 1/12 ml squared, I would add to it the total mass times the distance away from the center of mass. So that is an L over 2 squared. In doing that, right, L over 2 squared becomes L over 4. This becomes 1/12 plus 1/4 ml squared. 1/12 plus 1/4 is equal to 1/3. So this is wonderful, right? This parallel axis theorem, combined with the fact that we've got most of our common shapes already solved out for us, means that anytime we start to see something strange, anytime that we might see something strange like this, let's say that I don't know, we've got like a strange thing, somebody misses the mark and accidentally stabs the sphere through the very edge instead. That is totally fine to solve. We could do that easily. Our parallel axis theorem will tell us exactly what the moment of inertia should be. Oh, geez. It's been way too long since I've seen any of the Indiana Jones movies to make references on that one. So, this is kind of overlapping with our reading question as well. A little bit. How are you going to open a door? Let's be honest here. What's the best way to open a door? Which of these forces? Force 1? I think I'd agree. Why not some of the other ones? What goes on with that? If you've got the opportunity, try it right now, right? Go ahead and give it a shot. You can do this experimentally if you'd like, just to check to see some of the things that we've got going on here. Try to say, okay, I'm going to open my door, but I'm going to do it essentially, I want to do it at like 4-inch intervals. I want to start from the very edge, and I want to comparatively show how much force does it feel like it takes to open the door, or how fast does the door open if I poke my finger at it and I do it the same way every single time. Take 30 seconds if you'd like to try it real fast. Do it real fast. Just see a little bit of that comparison. Come back when you're all finished with that. Go ahead and give it a shot. We'll give it just a little bit for everyone. Parallax is there, I'm sure thing. Take a look at it. We'll wait just a little bit for those people to open their doors. I like to believe that, like the engineering dorm, suddenly there's like 20 or so different people opening their doors all at the same time. But okay, let's believe that people are probably coming back here. If not, I'll wave my hands around, so hopefully anybody that is looking at their screen, trying to figure out if we're back yet, knows that we are indeed coming back right now. But we kind of already know this one. Force 1. Of course it's Force 1. Force 3, maybe. Right? But the farther away I push from the hinge, right? So more towards Force 1 than Force 4, the easier the door is to open. But there's a few different ways that you can actually think about this, right? When you're talking about leverage, leverage is not a physics term, but torque is. Torque is a measure of essentially how much rotational force am I putting into an object. Typically, we use the symbol tau for it, not T, but tau, right? And I will try to write my taus out kind of like that. I usually do something like this. It's got like a little curved tail at the end and the swirly top. But looking at all of these different things, right? What we've got on this, of course, Force 1 is going to be applying the most torque. If you're talking about like Allen wrenches or something, right? There's always two sides to an Allen wrench. There's the short side and then there's the long side. One of those is going to give you a lot more leverage, ergo a lot more torque. You can get it a lot tighter with as not much effort. The whole idea here is you can even look at this from an energy perspective, right? It takes a lot more force from F4 to open the door the same amount because at the end of the day, it's more force over a smaller distance. The same work gets done. The same rotational energy gets put into the door. But in pushing it from the outside edge, we have to do it over a longer distance. But that means we need less force. So you can still get the same amount of torque. It doesn't really matter where you're coming from. You can still get the same amount of torque if you are applying different forces. If you have a fixed amount of force that you can apply, let's say that you've got, at least in my floor, if I'm wearing socks, my feet start to slide, right? I've probably got an upper limit of how much I can push before the door starts to make me slide across the floor a little bit here. But I would argue up until that range, I can make the torque the same on any part of the door. I just have to keep pushing with different forces each time. It is easiest to do on the outside edge because I require as little force as possible. So let me actually get into this, though, and talk about these things just a little bit more. These extra details that I'm looking for, right? Of course, this is our parallel to linear force. Torque is to force what moment of inertia is to mass, what all of these things, how they're supposed to relate together. I kind of lost the analogy at that one. But what we're looking at here is just all of the same concepts once again, right? Of course, I think you can probably already start to see where this is going. If torque is supposed to be the force, and moment of inertia is supposed to be the mass, then torque should be equal to I times alpha, just as force was equal to m times a. A torque causes rotation. The acceleration of that rotation, our angular acceleration, caused by the torque. Newton's second law, but for rotation. That's what this is. So, for all of these different things, I've got a couple quick questions here. Let's try this out. Of these three forces, which one is applying the most torque? Which one is doing the best job at actually rotating this object? Force 3, I'd agree. What about this object over here? Which one is doing the best job at rotating this object? Force 1, exactly. That's exactly what we're looking at here. The longer your lever arm, the more force you can apply, the more torque you can get. So, let's look at this in a couple different ways. At the end of the day, and I've got bad news bears for you right here, where have we seen this expression? Where have we seen an expression just like this? We should remember this one. We talked about it last time. Cross products indeed. Technically speaking, calculating torque comes from a cross product. Torque is a vector. I'm not going to talk about it as a vector quite yet, right? We'll get into that in a minute here. But we can talk about this first by describing this in three different ways. First, of course, with the cross product or anything else, what I'm basically doing is I'm saying, hey, how much of my force is actually going into rotating the object? R F sine of theta, if R is the distance out to where I'm applying the force from where it's going to be spinning, right? I've got my pivot point out to where I'm actually applying the force, that's R. I've got my force acting on my object at that point, F. The angle between those two, maximized when it's 90, minimized when it's 0, right? Go back to our door description. If I'm supposed to be pivoting right here, and I've got essentially my R vector pointing like this, here's exactly where we can use the same description, right? F2. This angle between F2 and R is 180 degrees. What is a sine of 180 degrees? 0. It does nothing for us. But when we look at stuff like F1 and F4, now that's a sine of 90. We have maximized the use of our force in creating a torque. F3, kind of a weird in between, right? It's got like a 30-degree angle going on here. So it is still effective at opening the door, but not as effective as F1. So that's the first way to consider this. The other way to consider this is to think about what's going on with each direction, right? If I have any of these forces, so F3 is a fantastic example here. There is a radial and a tangential component to this force, right? Of course, my tangential goes like this, my t-hat direction, my radial goes like this, my r-hat direction. Anything going in the radial direction is not helpful for actually spinning around. Anything in the tangential direction is going to spin us around. So if we take only the tangential component, then we have, as always, a perpendicular force to our radius. So that is the component, and you can even just simplify that. The tangential component of F is just F sine of theta. Or I guess in this case, phi. That's what I should be saying here. But it gets us to the same thing. Now, this last description is a little bit strange. I don't know many people that really like this one, but the other way to consider this is that there is, for any distance that we've got like this, r, we're essentially leaving force as it is, and we're saying, okay, well, how much of the distance, how much of r is going perpendicular to force? And that is just d, or d is equal to r sine of phi. That is our torque arm. If you think about it like that, I imagine there are probably some engineers that use that a little bit more. I have personally never been a huge fan of it, but whichever of these three descriptions makes the most sense to you, stick with it. Now, when we're talking about positive and negative, there's a direction associated with these things, right? Because something is either spinning clockwise or counterclockwise. If something turns around in spin, we can clearly see that. A torque must have been acting on that object. So, how do we specify directions? Well, we're going to follow our standards with the unit circle. That is, counterclockwise is a positive, clockwise is a negative. And if you think about that too much, you're going to immediately say, hey, wait a minute. If I look at a clock, and then I look at the back face of the clock, I would see it spinning in the opposite direction. What gives? What do you think that implies? Where is the direction actually pointing of torque? Does anybody have a good idea? Use some of our context clues. What direction, if I have a torque acting just like this on my cactus, what direction does the torque point? Don't say clockwise or counterclockwise. What direction should it be pointing? X, Y, Z, up, down, left, right, where? Perpendicular is not wrong, but it's not complete. Into or out of the page. And if we want to really contextualize this stuff, the answer, if we follow our right-hand rule, let's start with that. If we follow the right-hand rule, if I tell you right now that it is R cross F, what direction should that be pointing? Into or out? I'm going to see if we can get it first. I would argue out of the page. And let's try this. I'm going to take method 2 here. So what I'm going to do is I'm going to start with R. And of course, you've got to do this with me because I am flipped from all of you guys. So set down any pens or pencils you've got in your hand right now. I'm going to start by lining up all of my fingers with R. And then I'm going to curl my fingers towards F. My thumb points back out towards me, out of the screen, out of the page. Also, you might notice that that rotation, from our perspective, is counterclockwise. That rotation right there is positive. That's another way to tell. How do I tell whether it's counterclockwise or clockwise? Your thumb points in the direction that it goes. The spin around with the rest of your fingers also tells you about the direction that we call positive. The right-hand rule shows up in 1,000 different places in really strange ways. Every single time you're talking about rotation or cross products, the right-hand rule is there somewhere, hidden in the details. Hopefully, though, this is all to help tie this together a little bit better, weave all of these concepts a little bit. But I want to try this in a problem here. Let's imagine. We don't need to worry about these directions quite as much. I am interested in whether this is going clockwise or counterclockwise, though, from our perspective as we see it right now. Let's imagine we've got a 20-centimeter diameter disc shown below, and it's allowed to rotate through an axle through its center. Somebody stabbed it right through the middle, and they've started to try to spin this thing. But they've got 4 different forces, and clearly, if we want to rotate this thing, we have no idea what we're doing. But let's imagine we've got these 4 different forces. What is the net torque acting on this object because of these 4 forces? I'm going to say take the next 4 or 5 minutes to work on this one, and then we're going to come back together and see what you got. All right, so I think I'd like to start to take a look at this. We don't need to know anything about the moment of inertia here. That's not what we're asked about. If we needed to find the angular acceleration, then perhaps. But this is really, when we're talking about just what is the net torque, we're really looking for the net force. And if we're looking for the net force, then mass doesn't really matter, right? For acceleration, it might. We're not asked about acceleration. But let's go ahead and calculate this thing out. So let's go ahead and steal this picture first. And this is, of course, the easier way to do these things now. It used to be a Control-C would work totally fine for me, but no more. But that's all right. Something Microsoft did changed, or Krita updated something. I don't know. I can't tell. Some sort of mystery to me. But anyways, let's go ahead and take a look at this thing. I'm going to look at this thing piece by piece. Let's go ahead and label these. I'm going to call these things just kind of in a random order here. Let's do it in blue so it stands out. Let's call this force 1. Let's call this force 2. Let's call this force 3. And let's call this force 4. Is force 4 doing anything for us? No, it's a joke, right? It's not doing anything. It's pointing directly along. This is, again, if I'm trying to spin this circle around, force 4 is not going to do it for me. So now I need to look at all these other forces, though. 1, 2, and 3. So I'm going to say the net torque, or rather, let's just go ahead and start this one by one. So I'm going to say torque 1, right? This should be my distance, 0.1 meters, my force, let's do these in parentheses, 30 newtons, my angle between the radius pointing out to it and the actual force. These two are perpendicular, sine of 90. Which might as well be 1, right? This ends up being not 0.3, regular 3. How do I know if a force is going to do something or not? Because, I mean, like, I can take this from experience, right? Imagine a merry-go-round or anything else like that, any of those spinning things on playgrounds. If somebody just, like, slaps it head on, like, it's not going to spin. If somebody, like, you have all seen that one kid that just ran right into it, right? It didn't spin because of them. What you have to do is you have to be on the outside, trying to tangentially exert that force to get it to spin. So force 4 here, not doing anything for actually spinning it one way or the other. It has to be going like this or like this. Since it's coming directly out, it's not going to contribute to the spin. So that's our torque 1. Let's go ahead and look at torque 2. Torque 2, I've similarly got my distance, well, not similarly. There's quite a bit of dissimilarity here, right? My distance now is only 0.05. Oh, and it would indeed be negative. Thank you very much. Yes, because it rotates in a clockwise direction. So that should be a -3. But 0.05, this is a positive direction at this point. 0.05, same 30 newtons. Now I'm going to do with a sine of 45 degrees. And I actually don't have that number on hand. Give me just 1 second. Should be something like a positive 1.06. Finally, I've got tau 3. Now this one, similarly, is going to be spinning me counterclockwise. Counterclockwise being a positive direction here. I'm going to take my 0.05, 20 newtons. I look at R. I look at the force. Perpendicular between the two. Sine of 90. All in all, when I calculate this thing out, I should find something like, what is this? Just a positive 1, right? All things together, when we calculate this number out, and if we don't, there should be technically a 1 right there. What we calculate out at the end of the day is that the net torque should be a negative 0.939. And that would be, go ahead, what's up? Not for this, no. Not for this one. It's always going to be sine here because it's coming from the cross product. That's something that I've just given you right now. That's the definition of torque, technically. Yeah. Now, what's going on with these units here? Have we seen these units or something like this unit before? What do we think? Where was the last time I saw newtons and meters being multiplied together? Yeah. Our first instinct might be, hey, wait a minute, this is work. Right? Technically, but not quite. The units are a little bit strange in this one, and this is a big reason we keep the Newton meter separate. Technically speaking, on a very technical sense only, joules are newtons times meters. But in a case like this, we're not going to try and combine those things together, because when we're talking about torque, it's kind of like a little bit of a difference. When we're talking about work, it's a dot product, but when we're talking about torque, it's a cross product. The quantities don't quite intermingle in the same way. How do we know which direction we're rotating in? I would really just look at this and I would say, is it going clockwise or is it going counterclockwise? Force 1 was trying to send us clockwise. Force 2 and Force 3 were both trying to send us counterclockwise. And that's why 2 and 3 were positive, but 1 was negative. So watch out for these units. Don't write it out as joules. We typically write torque exclusively as Newton meters. And then, yes, it is just essentially, I need to look at the picture and I need to say, is this going to spin me clockwise or is this going to spin me counterclockwise? Multiplying by sign does not necessarily give us the direction. We need to use that from the picture. Picture tells us what direction it should be going. Right, because technically speaking, if we go back to that same description as before, when we're talking about any of these things, technically, it's R cross F, which would give us a direction. That would have a direction already associated with it. But when we switch the definition to being R F sine of theta, now, as we're seeing this, this would be saying, again, direction determined by right-hand rule. Which is much easier to just look at the picture and say, hey, is it going to be spinning clockwise or counterclockwise? But right-hand rule would tell us this in the exact same way, what direction it would be going. If we look at all of these things, like for F1, I could do right-hand rule to say from R cross to F goes into the page. F2 from R curl to F2 comes out of the page. F3 from R curl towards F3 coming out of the page. Right-hand rule tells us the direction as well. But it's probably easiest to just look at the picture. Is there anything else, though, or are we starting to feel a little bit more groovy with all this? All right. So, here's those nasty determinants again. Right? This is the actual definition. Whoops. This is the actual definition of the cross product. If we are being complete with everything, then technically speaking, the torque is indeed a cross product. This is just a simplification of the cross product, right? That difference between the two, this is an easier way to calculate these things, assuming that we already know the distance away and how much the force is, and then the angle between the two. If instead we are given some nasty things like a strange radius vector and a strange force vector, then it might just be that the matrixy version is much easier to solve. And I know it's a little bit tedious, but I promise it's the easier way to do things. So assuming again, of course, that when we have all of these things, we would have components in each direction, x, y, and z, both for the radius and for the force, or either or realistically. And then once we have that, I've already led on to this one, that once we have a net torque acting on our object, just as it was with force, if we divide the torque by the moment of inertia, we get the angular acceleration, right? This is identical to Newton's second law, but for rotation rather than linear dynamics. Is it all blending together into this wonderful soup of different concepts, right? All of these things, when we're talking about stuff like Dynamics never technically goes away. Dynamics never technically goes away. We're going to continue working with this stuff the entire semester. Right? Everything constantly builds. It's the wonderful race that is physics. So, let me move myself back down here for now. Let me talk you through an example. Let's imagine I've got a 2 kilogram, 30 centimeter diameter disc spinning at 300 RPM about an axis perpendicular to the center, right? So picture's the easier way to imagine this thing. This thing is spinning around that center axis. How much friction force must a brake apply to the rim to slow the disc to a stop in 3 seconds? So I'm going to work through this one. The first thing that I'm actually going to do, let me move this over to the side so that we can talk about this. So I want to stop this thing in 3 seconds. I think about that. I'm moving at a speed. Omega initial is 300 RPM. Omega final better be 0. There's a time that I need to do this in, 3 seconds. And I think back to my kinematics and I say initial velocity, final velocity, time. The only other thing that I would need to finish this equation out would be acceleration. That is, omega F is equal to omega naught plus alpha t. Now this is 0, and I would say, all right, well, alpha is not quite friction force, but in this case, I could imagine that it might be related. Friction force, they don't ask me about any sort of coefficient of friction or anything else like that. They are just asking about, okay, when this brake comes in, there's a friction force. What direction does that friction force go? Up, down, left, right, in, out. What do we think? I know that I'm supposed to be doing the example, but, you know, we can look at the picture. What's going on with this thing? As it spins around, what direction would the friction force want to go? Down. Yeah. And I'm even just going to consider this as the tangential kind of deal, right? I can see the disk wants to spin one way, so friction force better point the other. Friction. So then, because this friction force is acting on a spinning object, there is a torque associated with that, right? So my mass is 2 kilograms. My radius is going to be 0.15 centimeters. Whoops, not centimeters, 0.15 meters. I've already done that conversion. What I could say now is, all right, well, the torque applied by that friction force is going to be R times the friction force times sine of 90. Radius comes out like this. Friction force goes down like this. It's a right angle between the two of them. So there's my torque. How does that actually relate to the acceleration? Well, it does so through the moment of inertia. I can say that the torque is equal to I times alpha. So I could slap that in there. I could say then, okay, well then this is basically saying I alpha is equal to RF sine of 90. Or this is probably not the easiest way to do this one. Well, yeah, this is. Calculate out alpha from this. And let me go ahead and actually calculate some of these numbers here. So if I'm looking at this thing, I would say my 300 RPM, I want to convert that first, of course, into radians per second. 300 RPM is going to be 31.4 radians per second. Divided by my time of 3 seconds means that I should end up with a quantity that I can't see because of the hole in my calculator. 10.47 meters per second squared. Not meters. Not meters. Radians per second squared. We've got that quantity alpha. I. Where do I get that? Yikes. Oh no. This is a continuous body. Do I have to do an integral? No, of course not. Why would I do an integral when I have a perfectly good table of common shapes? What do I have? A cylinder or disk about center. So that is 1/2 mr squared is equal to my moment of inertia. So I would say 1/2 mr squared times alpha is equal to rf. Cross out one of the r's, plug in all of my quantities right here. What we should find at the end of the day... Sorry, I plugged in something very incorrect into my calculator there for a second. What did I do with this? That. Times our 0.15 should give us something. Again, I keep screwing myself up with the bad holes in my calculator. 0.79. Is that right? That sounds a little bit strange. Hang on. What did I do here? Give me one last second. Whoops. 1.5. 1.57. Barely see it in there. But it doesn't take that much. Can I move my face cam? Yes, I can. Sorry, I got a little bit carried away there for a second. Get in the heat of the moment solving physics problems like this. Put myself up here for now. So, at the end of the day, this is really not that different from any of our old dynamics and kinematics stuff. All of the same concepts apply. We've just got a couple new ones sprinkled in there, and we've got to calculate some more values than we're used to. But conceptually, all of our equations line up exactly the same as they would have before, right? We had our kinematic side of things. We had our dynamic side of things. We combined those two together to find our final answer. No different. Think you're ready to try it on your own? Not waiting for an answer on that one because we're going to try it anyways. Let's imagine here. A negative 10 joule Newton force is exerted on a particle at R. What did it say on the bottom right down there? That was supposed to be a 1.57 newtons is that quantity. Let's imagine this, though. We've got this force acting at this radius. Draw it out. Start with that, of course. Draw it out. Find the torque. Start by doing an A cross B is equal to AB sine of theta. Make it a little bit easier, right? Take the magnitudes, take the angle between the two. Once you draw it out, the angle should be pretty clear. Take those two, use right-hand rule to do that. Then use component method. Prove that they are equivalent. Prove that either way you take this, whether you're taking the AB sine of theta or whether you're actually doing the matrix, gives you the same result. I'm going to say, let's go ahead and take the next, say, 4 or 5 minutes to work on this one. And then we'll all take a look together. All right, so let's start taking a look here, and let's see what you got. So, in order here, I've got my two vectors. Let's go ahead and just write those out, and let's start from there. And let me move myself down first, right down to here, so that way I'm not covering up any of the things that I need to. We've got that our force is going in the negative j hat direction. Negative 10 j hat. Our radius +5 +5. Both in meters, which is actually an important detail, right? If that was in centimeters, that'd be a little bit of a different story. Direction would be the same, but our quantities would be different. So, already given in meters, I will even go ahead and write out newtons. 5 I hat plus 5 j hat. Again, both of these in meters. Nice and easy. So, with that alone, I can draw this thing out pretty quickly. I'm not even going to do it very large. I don't think we really need to. Let's go ahead and do my force in a light blue. I see that is pointing negative 10 down, just like that. Let's imagine that it actually lines up on the axis. I think it shows up a little bit better like this, something like that. That is my force vector. R, 5 up, 5 over. Bam, just like that. So, looking at this picture, just seeing these vectors as we've got and looking at our picture, what is this angle between the two of them? What do we think? Yeah, 45 plus 90. I'd agree. 135 degrees. Now, one of the things that we do technically want to be a little bit careful on here, one of the details that's probably not quite clear, 135 degrees is totally fine to work with. Technically speaking, when we're doing a cross product, we can have these things. Well, I'm not even going to get into those details. Never mind. 135 degrees, that's totally fine. 135 degrees right there. That means that if we're trying to take this thing with the right-hand rule method, what I'm going to start with here is we'll say that our torque is equal to, let's see here, R F sine of 135 degrees. I already know that F is just 10. R, slightly more complicated. This right here tells me that R is going to be 5 times square root of 2, which if we want the actual value for that, that should be something, oh shoot, I'm blanking on what my root 2 value is, 1.44 times something. 7.07 though. It's a good value to use for that. Multiply all of these things out. We should have our torque times our force times sine of 135 lands right at 50. Now, the question is, clockwise or counterclockwise? 5 root 2, that is the magnitude of R. If I've got 5 and I've got 5, Pythagorean's theorem would give me 5 root 2. I'd agree clockwise. I would certainly agree clockwise. And I can do the right-hand rule to confirm that. Start from R, curl towards F. I go into the page. I spin around clockwise, that direction. So I'm going to say that this should be 50 in the, let's say, negative k hat direction from right-hand rule. We have found the quantity, then we have to determine whether it's going to be positive or negative by whether it is turning clockwise or counterclockwise. I see this thing turning clockwise. One of the easier ways to do this, if you're a little bit mystified at that one, I think the easiest way to do this is to go ahead and take the F vector, and I would even just kind of move it over like this. Put it right here. Can we all agree that that force acting on that radius is turning that thing clockwise? I would think so here. So that's why I've called it the negative 50, though. Because it is turning clockwise, it should be a negative value. That is my direction associated with that. Negative k hat is technically speaking the direction, or I can just write instead of negative 50, or the negative k hat. Oh no, I selected a bunch of things. The other way that I could write this is just to say clockwise. So this was part of it. And clockwise here means negative to equal to negative k hat. And let me show you that by let's do the matrix method real fast. This will be easy, I promise. If we take R cross F, here's what we're going to get. Big old matrixy. I hat, J hat, K hat. My R vector, my F vector. Go ahead and finish this thing out. I'm going to do that Kramer's method again, the fancy way to do a 3x3. This is the easiest way to set it up, I think. Take the down diagonals, add them all up. Take the up diagonals, subtract them. Now, if I go through these things piece by piece, I would say first one, 0. 0 I hat. Cool. Second one, 0. Cool, cool, cool. Third one, all right, that's actually something. That's k hat. Let's go ahead and do it like this. 5 times -10 times k hat. Subtract the up diagonals. So I'm subtracting 0k hat, and then I'm subtracting 0i hat, and then I'm subtracting 0j hat. It's a lot of preamble, a lot of setup just to end up with 5 terms that are 0 and 1 term that actually has a quantity. But when we do this, when we plug everything in, we find our final answer should be something like -50 k hat. Exactly the same thing as as clockwise. So that's why I made that distinction. That is where we're talking about all of these things. How do I tell what rotation is and everything else? How do I compare these directions? If it's going clockwise or counterclockwise, I'm telling you which one is positive, which one is negative, counterclockwise being positive. But the answer for why it is, how you can actually show that for yourself, if you are a little bit fuzzy on just remembering the definition, is that the right-hand rule tells us. If it's going along the positive z-axis, if you're looking at it dead on, the z-axis is pointing directly at your face, it's going around counterclockwise. If you're looking at it going inwards, the negative z-axis, it's going clockwise. Right-hand rule relates those for us. It's a wonderful tool to have. Right? And there's not even any equations that we have to write down for this thing. Are we ready for one last hurrah? Let's imagine I've got a 1 kilogram ball and a 2 kilogram ball, and I am connecting them to a 1 meter long, rigid, massless rod to form what is probably one of the worst dumbbells. Right? I guess one of my arms is much stronger than the other, and I would like to work them both out at the exact same time. Let's imagine here, the dumbbell is rotating clockwise about its center of mass at 20 RPM. Clockwise and -k both mean going into the page, indeed. Yes. So here's where we're combining all of our details from last lecture, or some of them at least, and a lot of the details from today. First, you need to find where the center of mass actually is. Where is that pivot point that it's rotating around? Second, you need to find the moment of inertia around that center of mass using our moment of inertia equation that we had seen from before. It does not show up on this slide. This slide will not help you with this. You've got to actually use the formula. Third, let's imagine we need to find what constant torque will bring them to rest in a time of 5 seconds if it starts at 20 RPM. So, we're going to take the next 5, maybe even 6 minutes to work on this one. We'll go ahead and say 6. Give it an even 6. And then let's come back together and see what you got. All right, are we ready to start taking a look here and see what we got? So here's what I'm going to do. I need to draw out a good picture first, and your picture might look different from mine, and that is totally fine. I'm not at all worried about it. Here's what we're going to need, though, right? Here's how I'm going to draw it, at least. I'm going to start with the 1 kilogram ball on the left side, the 2 kilogram ball on the right side. Go ahead and draw my axes first. Kind of imagine it, and let me do it like this. This is probably, I think, the easiest way to do this thing. Let me call my y direction goes like this, my x direction goes like this, and I'm going to draw this first. Here's my 1 kilogram. We'll even color this thing in, right, just for the fun of it. Then, let's go ahead and take the 2. We'll have it be over here. Something like that. We'll again fill it in just the exact same way. Looks good on that one. And then we've got some sort of massless rod of 1 meter connecting the two of them together. So I'm going to draw that in like this. The reason that I've done this is because I need to figure out where is the center of mass relative to these two, right? It's going to split the distance somewhere in the middle here, I assume, I guess. Right, there's a couple other things that could happen in that one, but I'm going to guess that the center of mass is right between the two of those. So I need to figure out exactly where that is relative to each one. So here's what we're going to do. Can we all guess that it's going to be right here or so? right? And you might be able to look at this and immediately guess. You might be able to tell just by kind of looking at this picture and thinking about it a little bit. You might be able to figure out where that center mass is, but I do want to calculate it just in case. When I have done it like this, what I'm saying here is that this is at 1, 0. This is at 0, 0. So my x center of mass is at some, call it x center mass coordinate, 0. Now, to actually calculate that out, where is my center mass? Of course, I take my center mass equation. 1 divided by the total mass times the individual pieces here. X times the mass. So I start with the first one. The red ball has a 1 kilogram mass, has a distance of 0, or its placement on the x-axis is 0. The blue ball, mass of 2, distance of 1. My total mass, 1 plus 2. Might as well even just go ahead and erase that, right? We don't need that there. We can look at this and say, hey, that should be 3. That means my center mass is right at 2/3 of a meter. So now that we have that, we're going to use this information, right? This tells us exactly where this thing is at. But the next thing that we need to find is the moment of inertia about this center of mass. Moment of inertia. Of course, my big equation, the general equation that we could use here, is every single mass and every single radius away squared. All of that stuff tied together if we really wanted to get into it. No, this certainly does not work on a bench press very well. Right? And of course, it's because of the torque. It is one thing to try and push up the weights in the first place, but it's a completely separate thing to also have to be counterbalancing that with the other hand. So please don't try this out for yourself. Or if you do, stick with these masses. 1 kilogram, 2 kilogram, that's not much. That's probably a reasonable thing. You can see pretty quickly why this doesn't work very well. But let's take this. So we've got this equation. Let me take each mass. So I'm going to start with mass 1, and then the distance away from the center of mass squared. This is not the same thing as the x-coordinate, right? This r value right here, we might remember distance from center of mass, C-O-M. So with all that stuff in mind, we're going to say, all right, well, that one surely should be 2/3 away. The blue one is going to be only 1/3 away. 2/3 squared plus 2 times 1/3 squared. Now that we have all of that stuff in line right here, calculate this thing out. This is going to become 4/9 plus 2/9 for a total of, conveniently, 2/3 again. But now my units are different. Now it's kilogram meter squared, right? Because this is moment of inertia. It's a different quantity. It just so happens that the number is exactly the same. So far, so good, right? That is parts A and B down. Now, the last thing that we need to find is we know that this thing has some sort of initial speed. And let's go ahead and even say it doesn't matter which direction it's going. We're just looking for net torque. But let's imagine it's spinning around like this. So, out of all my information that I might have right now, I've got a small little kinematics problem. I would say that my omega initial is something like, what did we say, 20 RPM? My final, 0? Or let's even say -20, because I've got it drawn going in the negative direction, don't I? Let's say -20. Doesn't really matter which way it actually goes. We're just looking for a quantity anyways. I know that this has to happen in a time of 5 seconds. I have my moment of inertia. I'm looking for a torque. I could say that torque is equal to I times alpha. And we have just calculated out that moment of inertia. The only thing that we need to find to make this thing work is this alpha quantity right here. Alpha, of course, being the acceleration, comes from our kinematics. Omega F is equal to omega initial plus alpha t. Omega final is 0. Alpha is the initial omega divided by t, or the negative initial omega divided by t, should give us a quantity like 0.419, and that is, of course, in radians per second squared, we need to have converted our RPM into radians per second. Go ahead and do that right there. That's what we should get if we convert that properly. Negative 2.09 radians per second. We have alpha. We have the moment of inertia. We plug both quantities in. We should find at the end of the day a quantity like 0.279 Newton meters. And there we have it. How is that feeling? Do you feel like you're ready to take on the world? Go solve out some problems on your own? And the answer is, of course you are, right? Because we're having a great time with this. Take it as a bit of a victory lap right now. You know how these concepts work together pretty well at this point, right? You have done dynamics and kinematics and all of that good stuff, and I'm trying to tell you right here, this is not really any different. All of our old concepts still apply. We just have a couple new ones to add on to it. But with those new concepts, it's mostly like a victory lap. We're looking at all that old information one more time, and we're saying, yeah, we've done this before. This looks familiar. Even if it is new variables, it's still the same old concepts. So, that's all I've got for the rest of today. Right? We're all clear with this one. You might need, I think we've got it in a couple different places. It shows up in the book as well, but you might need this slide. This will certainly help you with some of your problems. It is right here at the end of the slides. Just a little bit of a reference for all of these common shapes that we would need to use. But with all of that stuff, you should be all ready to start diving into your next set of homework problems here. But as always, team, thanks for being here. I, of course, always appreciate it. And I'll see you next time.